Hi everyone. Thank you first of all for being here. Welcome to DevNet 2001, working with and building for non-x86 compute architectures. That's the title. Okay, not for me, sorry. So my name is Jens de Peut. I'm part of CX EMEA. I'm a technical leader in data center. Day-to-day task is mainly situating around Hyperflex, Cisco's hyperconverged infrastructure. I've been with Cisco since 2015, based in Belgium, so this feels a bit like home here. So first of all, I would like to ask you to try and keep, if you have any questions, keep them until the end of the session. You can also ask them in the Team space, WebEx space, which you can join from the Cisco Live mobile app. During the session, after the session, even after Cisco Live, I will try to give you an answer. And of course, if you meet each other here, more than happy to talk with you about compute architectures or any DC question you might have. So you can also find the presentation in the app. I will post it in the room as well in case you don't find it or you have troubles with it, so to make sure you have it. On the menu today, I will start with a bit of a background. We go back very high level, look into compute architectures. Where are they? What's the history of that? And where are we today? What's the challenge with the situation we are in today? That mix of architectures. And then, of course, I wouldn't have much to say if I only talk to you about problems or challenges without any solutions. So I will try to explain you how you can overcome or at least deal with that situation we're in. And I will end up with a summary where I will try to, in one slide, summarize what we've been through. So taking that step back to compute architectures, in essence, this is what the CPU is doing. It's a lot more complicated today, a lot more optimization, but it has been like that from the start, and actually it is still like that. We have a certain input, it gets stored in memory, and then when the processor has to work on that operation, it takes it in a register, decodes that instruction into some sub-steps which that CPU understands, it executes those steps, and the result gets saved back in memory. Then there is another instruction, or it goes to output. Of course, this is oversimplified, but in essence, that's what's happening in your CPU. And how that happens is determined by your ISA, your instruction set architecture. So that defines how your instructions are processed, how memory is accessed, how to deal with I/O. But fortunately, we don't have to deal with that directly. For that, we have a higher level programming language which abstracts that. That means that we can program in one language and use that on different ISAs. There is a compiler that takes care of that, and then that ISA on its term is taking care of the lower level steps up until the actual physical transistors on the chip. So there are different of these ISAs. This is small, and it's not the intention that you can read it. Just to show you, most of these are not used anymore today. I just looked up on Wikipedia compute architectures, and historically, this is what's been there. So where we are today actually comes largely from iterations we've been through and learned from up until an ISA or a compute architecture which is usable today. And that today looks a bit like this. So I know there are more compute architectures active today, but the two major ones are x86 and ARM. x86 been around the longest from the Intel 8086 and evolved from 1632 to the current 64-bit version where we are now. x86 is a CISC type of instruction set, meaning complex instruction set compute. I'll go back to that in the next slide. And then we see arrays of ARM as well next to that. ARM, big difference is it's of a RISC instruction set type, so reduced instruction set compute. Started with Acorn a bit later than x86, but went through that same evolution. Currently, we have 64-bit ARM as the most popular version. Of course, there are popular examples, the upcoming Ampere Altra, Snapdragon in phones, but of course, Apple's M1, M2, disrupting the desktop, the workstation market really a lot by making that bold move and showing us that ARM is a valid alternative there as well. I put Power here as the third one. It's on the decline, I would say. Maybe by the next time I deliver this presentation, RISC-V will have a place there, because that's a RISC architecture which is gaining a lot of popularity now as well. But in essence, what we have today, the current situation, we have ARM versus x86. And what this comes down to is RISC versus CISC. RISC being that reduced instruction set compute. That means you keep things simple. You have a few instructions in hardware in the CPU. If you need to do something complex, you translate that in multiple easy instructions. You go through it multiple times, but it's quick. With CISC, the approach is the opposite. You try to make as much complex instructions in hardware. That means you have a one-on-one translation. The compiler almost doesn't have to do anything. It just translates to that instruction which is there in hardware. On the side for RISC, the compiler has a lot more work. You can optimize a lot more because how you split up that complex operation in simple instructions makes a big difference. Because of CISC, you have a lot of more transistors. You have a bigger size of CPU, and also that comes with a higher power consumption. Traditionally, because we can make that one-on-one translation, we have less overhead, and x86 still is going for peak performance, while ARM is going for energy efficiency. Today, and that's what Apple has been proving us, for workstations and servers, there is no longer a technical limitation. We can reach the same performance in the same size with the same power consumption, pretty much equal. The main reason why we choose one over the other is mostly code compatibility. It's that legacy that we have. People are comfortable with it. We have that software on that platform. Today we see x86 in workstation servers and in desktop still is dominant there. And that makes sense. We have the power, we can cool enough, and performance is a critical thing, like in a data center. For embedded or mobile applications, RISC makes a lot more sense, right? We have less power usage, it doesn't become as warm as an x86 CPU, and in most of the cases, we can do with less performance there. So what's the problem with that? The problem is that current situation where we have that mix of architectures. That means if you develop something on one platform and you do this as you've always done, you transfer that binary, if you compile something, to another platform, it will not run there. It doesn't understand that code, which is the result. That binary cannot be executed on that CPU architecture. And even if you can actually develop something for the other platform, like a cross-compilation, you can't test it on your own machine. So that brings another challenge with it. So what does that mean in practice? Well, obviously, for your code which you write yourself, you have that problem which I just explained. So that also applies to certain pieces of automation, also to containers. A container is architecture specific. So if you develop a container image, you move it to another site, it won't be able to understand that, won't be able to execute it. And even if you can, it's hard to test, it's difficult to test on your developer machine. For common tools, in theory, that problem doesn't exist. You have a package manager, you fetch the tool which you need from the package manager, including its binaries. But in practice, if you work on embedded devices, you work on edge devices, network devices, you often come across a strange Linux distribution, something custom. You have missing packages, maybe not even a package manager, no dependencies, or the versions are so old they don't have the features which you're looking for. And also in certain situations, you come across something where there is just simply no connection to that repository. You have a dark side, and you need an easy way to have a tool, a certain piece of code on that platform which you, for example, want to troubleshoot. So how is that relevant for Cisco, right? Everything I said until now is not Cisco specific. But we do allow, and it comes under a lot of names, depending on which technology you're in, we do allow to run your custom code or containers on our edge and network devices. This comes as IOX and app hosting for enterprise, guest shell, guest OS, open agent container in data center, but in essence, it is the same thing. We allow to run pieces of code or containers on our hardware. And that hardware comes on different CPU architectures. So if I would have given this 2 years ago, I would say, okay, we almost always have a developer machine x86, but now, even if we develop for a platform on x86, it can very well be that you're using an Apple M1 or M2, which is ARM. So the problem already also exists there, or so is more common today. Typically in data center products, again, where we have that power, where we have the ability to cool, and where peak performance is important, we run x86. In service provider, there is a mix of typically x86, historically 32-bit ARM, currently also 64-bit ARM, and in enterprise, you have the whole range. We have x86, 32, 64-bit ARM, and even some devices with PowerPC. So what can we do about this now? What are the solutions, or what is the solution? Well, it depends, which is typically an answer you get on any IT question. It depends on your use case. It depends on which language you want to use and what you want to get out of this. Is this a one-off, a small tool you need to troubleshoot something one time? Or is it actually an application which are developed and want to maintain over a longer time? And there, again, I will bring up a few solutions, but you can actually pick and choose, combine them together, and automation is your friend there to make your life easy, at least if you want to do this over a longer time. So solution number one, it might be obvious, but you can just use the destination architecture. Let's say you want to make something for ARM, you only have an x86 machine, well, do it on an ARM machine. And first thing you think about is just a physical device, like a Raspberry Pi, for example. But what is very current now as well is that all major cloud providers offer you the ability to use ARM in the cloud. So a valid alternative, I would say. And actually, I gave this presentation about 6 months ago. There were two cloud providers which had this publicly a bit hidden on their website. Google didn't have it yet. Azure had it in beta. And now I checked again, and to my surprise, all 4 major players have it wide in the open on the first page. We have ARM, use it please. So this tells you a lot about how the demand grows for this kind of things. Solution 2 is to use platform-independent languages. And that name, that definition, is a bit vague. It doesn't apply to all. But the idea is that you have an interpreted language. It could be compiled, but resulting in something architecture-independent. If we take Java, for example, which you typically compile into a class file, the result is architecture-independent. It is it's a piece of bytecode, and only at execution time by the Java virtual machine, it gets translated into something ISA-specific, CPU architecture-specific. Python works actually in the same way. There is a Python virtual machine, although better hidden or less something you have to deal with than in Java, on the background, and that does exactly the same thing. You can use PHP, Bash, Tcl, those are examples of the same. So, small demo. I have a certain piece of Python here. It's an improved version of a hello world because it says hello devnet. That's better. And we will have that same piece of code, run it on x86. Hopefully, we will see hello devnet. We copy that same file to an ARM-based machine, and it should do exactly the same without the need for us to change anything. So let's give this a try. So on the left side, let me make it a bit bigger. On the left side, I have a x86 64 machine. On the right side, I have a 64-bit ARM machine. So I have that piece of code here, which I shared in the presentation. Hopefully, it's readable. And right here, I don't have anything. But to prove you it's exactly the same piece of code, I will copy this over to the other side. So on this side, I have exactly the same piece of code now. So if I execute this here on this x86 machine, you can see this is working. On that 64-bit ARM machine, I didn't change anything, the same piece of code. I didn't compile it in a special way. That's just by how Python is translating to machine code, by that design. This is pretty portable. Okay, this doesn't take into account differences between operating systems or maybe lower-level system calls, but you get the idea. In a lot of cases, this is a valid solution. So third option, if we cannot use this kind of language and we actually need to compile because you might need the speed, or it could be that you want to use a open source tool or a tool which someone else has written and it is in a language like C, C++, Go, Rust, that requires compiling. Well, then one option is to do cross-compiling. That means you compile on one architecture for another. As I mentioned, that last sentence here, your build platform cannot run the resulting binary. So it's a valid option to produce that binary, but to test it, you will still need a machine running on the other platform. And some terminology that comes with that, I personally find it confusing. So you have a build platform, that's the platform where you build on, so far makes sense. And then the platform you build for is not the target, that's the host platform. So I try to pay attention to what I've said until now and use destination architecture instead of target architecture all the time. If you talk about target platform, you're dealing with creating the cross-compiler or compiler tools themselves. So you have a certain source code, depending libraries, you push this through a cross-compiler, and as a result, you have a binary which should be able to run on another architecture. So demo again, I prepared my machine, I installed a cross-compiler for 64-bit ARM on that x86 machine, installed the rest of the tools, so assembler, linker, binary tools, all in one package, also for that destination architecture. What will I do? I have again this very much improved version of Hello World, but in C this time. I will compile it with the cross-compiler. My result will be a binary for 64-bit ARM, and then I will see on which machine I can run that. Clean this up here. So that's my piece of code in C. It's about the most simple you can go. So I call my cross-compiler as input. I have that piece of source code, and as output, I have this file. So if I check which type of file this hello world-arc64 is, you can see this is a piece of code compiled for 64-bit ARM. So far, so good, but if I try to run this here, this machine has no idea how to deal with this binary. If I copy it to the other side, I have here the same binary now. You can see the checksum is the same. I can just execute this here and it works. So you see, this is an option to create the code for another platform, only it's not possible to test it. So that was pretty simple. So that's what we did. We had 64-bit x86 64 machine. We used that to create that binary, couldn't run it on that platform. After copying it to the destination architecture, the architecture where we built for, we were able to run it. That's a pretty simple example, but what about dependencies? Right now we had a simple piece of code, we had no dependencies, and remember in the beginning I mentioned we can't, or we could be in a situation where we can't fetch those dependencies from a package manager. So if we have dependencies, we also need to cross-compile these for our destination architecture. And by default, in Linux at least, we use dynamic linking. That means all dependencies, as much as possible, you keep out of your binary because they can be used by another tool and you save space. You have only one library to upgrade. They are architecture specific. So what if these are missing, or what if you deal with such an obscure platform where there is no package manager or all of the dependencies are seriously outdated? Well, therefore, we have static linking. Static linking means you have a binary which also includes its dependencies. This is not recommended for day-to-day use because it's unsecure. If you upgrade or update libraries, they will not be upgraded in your binary, of course. So you potentially have an older version which has a security vulnerability. It can lead to incompatibility, especially if you talk about lower level system calls or conflicting with current versions which other tools are using. And of course, your binary will be larger because it includes those dependencies. It can also be tricky, especially with libc, and that's a popular library. You might run into problems, but there are alternative libraries like Muscle. I didn't invent the name, sorry for that. And I put there, it works for me. So it is not recommended, but if you're in that situation where you really need to troubleshoot a certain platform, and I took this with examples in practice where I needed something like strace, TCP dump on a edge device which didn't have those tools, and I also didn't have dependencies, I didn't have a package manager, so I needed a way to execute those tools and actually have a single binary file I could easily transfer over and use. So as a demo, I will do exactly that. I will take the source code of TCP dump, which depends on libpcap. Probably that's something some of you already saw or worked with. So I already downloaded these two source codes. I will extract them, and then we will do a cross-compiling with static linking. In this case, I will not pass every source file to that cross-compiler. I will use make, which is a popular option to actually build open source tools. So you run /configure, which is a script that checks your environment. It creates a make file, and then by running make, we use that make file to do the actual compilation and all of the dependencies. I will do this first for libpcap, and then I will do this for TCP dump, which should include libpcap inside that single binary. The result should be a single file, which I can copy over to that 64-bit ARM machine and run TCP dump. So cleaning up first. And then here I have these two files which I just downloaded from the website of TCP dump. I will extract them. So I start with libpcap, and the first thing I do is setting a variable cc. That variable will be used by that configure script. It will actually check did this user configure cc as something different. So that will be the cross-compiler or the compiler which I'm using. Then I run this configure. So what do I have here? I have /configure, my build platform, x86 64, my host platform, remember the weird terminology, 64-bit ARM, and I give a flag to the linker that I want to do static linking. So this checks the system for whatever I have, which tools I have, and the result should be a make file. It's a bit unreadable, and the time is wrong, but this is a file which just got created now. And this is served as input for the make command. So make will read that make file and do the actual compilation. Because it's zoomed in, it might be a bit confusing, but you can see here that all of the pieces of code, all of the source code, actually gets pushed through that cross-compiler. That's because I set that cc value to exactly that muscle cross-compiler which I mentioned. And as a result, we have here, let me move this a bit maybe. We have libpcap.a and .so. These are my outputs. This is now my compiled dependency for 64-bit ARM. So the next step I need to do is do the same for TCP dump. So my cc variable is already set. I run the same configure with build and host architecture set, linker flag as static, and the first step is to create that make file. And we can see here, it passed by a bit quickly, but we can see that this configure script detected that it found libpcap locally, and that will be the version that I will include in my statically linked binary. So all we need to do is make, and that will do the actual compilation. In the meanwhile, here on the right side, my 64-bit ARM machine, I will show you that it doesn't have that dependency. So So I'm searching in the whole file system for any file starting with libpcap, just to show you I'm not lying, I'm not inventing something, but we don't have libpcap on that right side. In the meanwhile, my compilation is running here. It's about to be done, and we can see on that left side that there is no libpcap there. The result of this here is a single file. So we see TCP dump, that's a single binary file. It has all its dependencies, libpcap, inside of it. If I check which dependencies it has, so I check which dynamically linked dependencies are there, we can see this is not a dynamic executable. So it doesn't search for any other binaries. So if I try to run it here, of course, again, same problem. This is designed for 64-bit ARM, so my x86 machine, of course, doesn't know how to deal with it. And if I copy it over, if I copy it over to that 64-bit ARM machine, we can see it tells the same thing. It says statically linked. That's basically the same as it's not a dynamically linked executable. And here, we'll try to first execute with -h. So we can see that we understand this code. And of course, if you want to actually test if this is working, we should see, or we should be able to capture the traffic going on here. And there it is. So you can see this is pretty powerful, right? I didn't have on that machine a package manager. I didn't have the tool I needed. I created a single binary file, which is extremely portable. I can copy it over with a USB drive or whatever, and I was able to use it to troubleshoot whatever is going on here. Okay, so that's what we saw. I did that cross-compilation with static linking. It didn't run on x86 because it's designed for 64-bit ARM, but it did run on that 64-bit ARM machine, of course. So more options here. Another popular option is emulation. So on my machine which I'm built with, I can emulate another architecture. And a powerful tool to use with that is QEMU. QEMU can supports a lot of architectures. So x86, of course, ARM, of course, but also Alpha, MIPS, RISC-V, PowerPC, and even something like System Z mainframes you can compile or you can emulate with QEMU. Two options there. First one is to use virtualization. So you actually start up a VM on top of QEMU and you install a kernel or an operating system and do exactly the same as that first solution. You pretend like you build and test and compile on your target architecture. But even better is user mode emulation. So there you combine QEMU with something called binfmt. It's a feature in the Linux kernel that will actually detect if a certain binary is for another architecture. It will not execute it natively. It will send it to QEMU and emulate this architecture. So this has a big advantage because, first of all, it's typically used to build containers for another architecture. But what I've been doing until now, like doing that cross-compiling, it means if I have QEMU and user mode emulation, if I did that /TCP dump, I can actually execute it on my built machine. So in that case, it will be emulated, but at least you're able to test it. Again, small demo here. So in preparation, I installed Docker. I will install those QEMU emulation binaries. And why didn't I prepare that? Well, otherwise I couldn't show you that I couldn't execute that cross-compiled binary, of course. So I installed QEMU user static, and binfmt. And then we will have a look, and you can see there's plenty of architectures which you can emulate. I think the list even got bigger. Once that is done, I will run a Docker container. So I'm taking 64-bit ARM Alpine base image from the repository, which should not be able to execute on my x86 machine. But in this case, we will be using that QEMU. So BinFMT will detect that, send that to QEMU, and we are also able to see that when we look at the processes running, but that should be clear during the demo. Okay, so let me first install these packages. Sorry for that. Always happens with demos. Works better if you have a network, right? We try again. Okay, that was some quick troubleshooting. Sorry for that. I actually tested it right before I started, and as is always the case, demos are supposed to fail. So, like I said, I'm downloading those packages now. I will install them. I will show you which of these user emulation binaries we have, and then I will run that Docker container. Almost there. So what this installed is that binfmt, that kernel extension that will actually detect which kind of binary I have. And this is smart enough to know to which emulator I should send it. So QEMU comes with this set of architectures which it can emulate. So if I execute one of those binaries, binfmt will detect this is not for me, this is not native. It will send it to one of these static emulation binaries. So as I showed you in the slides, I will now do a Docker run. I need to pass that static emulation binary to the container, and what I'm starting with is that ARM64 base Alpine image. The container started here, so we turn that image into a container. If I check which architecture that container thinks it is running on, you can see it thinks it is on 64-bit ARM. If you look in the background, so let me duplicate this session, make this bigger. We can see, so I'm running SH in that container. It's very bare bone, it's very small, but we can see here that SH is not executed natively. It is running through binmft on that emulator, that QEMU emulator. And this is very powerful to create containers for another architecture. So that brings me to the next demo, where I have a Docker file. I start again from that 64-bit ARM image. So the goal of this demo is I will use my x86 machine, and I want to create a container which I can run natively on ARM. So I don't want to do anything on that ARM platform. I don't have access to tools. I just want a container image which I can run there. So simple example, I copy that static user emulation binary to the container. I install Node.js. I copy a simple example. I expose port 1337, and then that's the process I start in the container. I build that on my x86 machine, and then I will try to run it, and we are able to run it on both sides. We can run it on our x86 machine, emulate it, and we can run it natively on our 64-bit ARM machine. So to save some time, I prepared this, so I have this devnet.js here. You can see an image ID. I have it on this side as well. Let me move here. First, stop that container. So I have this image ID here. You can see it's the same ID. I'm not lying. That's the same image. If I look at for which architecture this is made, I can see 64-bit ARM. I used exactly the example as in the presentation. Of course, if I do the same on this side, it results in the same result because it's the same container image. So on this side, let me execute it. So I just do a docker run devnet.js. It's starting on this side. Get the same thing. So both of these are starting Node.js. It's the same image. I can use it portably because I use emulation on my x86, and I can use it natively on my 64-bit ARM machine. So if I go now to my browser, this left side is my x86 machine. Right side is my 64-bit ARM, and you can see this is running exactly the same. I asked the container, which architecture are you on? That last line, both of them say ARM64. How do I know that left side is emulated? Well, the name of my kernel still includes its own native architecture. So this gives away on that left side that actually I'm not running natively. I'm emulating. The kernel is a x86 kernel, but emulated on top of that, we run our container in 64-bit ARM. So that's exactly what we did. That's how you can see that this is emulated, but you can also see this allows me to create on my x86 machine an image, a container image, which I can run on any other platform, and I can also test it by using emulation on that built machine. So remember those binaries? I actually gave it away before already that we could not run. Well, after we installed QEMU and binfmt, the kernel will detect that this is a binary for another architecture, and I can just run it, and my improved version of Hello World will actually run on my x86 machine as well. And so how do you use that now in practice? Well, you pick and choose, and you combine the things. So you can use cross-compilation to build a binary. You can use emulation to test it. You can use emulation to build, test it on a destination architecture if you want. For example, if you use GitLab, you can use runners for each architecture. Or there is also something called Docker build-x. And in the background, this automates the stuff for you. But in the background, it does exactly what I explained. It uses QEMU, it uses binfmt, and you can build actually on different machines. So you can use those cloud instances, for example, to build other containers in an automated way. So we're about to be at the end. As a summary, the situation which you are in today, more than ever due to disruption which Apple pushed to the market, is that we really have a mix of x86 and ARM. We no longer have typically a workstation on x86, maybe building for another architecture. Even if you build for x86, in this world today, it can be realistic that you need to go cross architectures. You can code platform independent. If that's an option, that's the easiest. You can use the same code on your build machine. You can use the same code on your destination architecture, very portable. If that's not an option, you can use cross-compilation. You can use static or dynamic linking depending on the situation which you're in. And emulation is a very powerful tool which you can use to build containers, but also to test those other binaries or tools that have been built for another architecture. And of course, combine everything with automation. If this is a longer running process, if this is a tool which you redeploy often, that's what you should use. If it's a one-off, of course, you can do, like I did in the demo, build that result, single binary, which is a powerful troubleshooting tool on your target destination architecture. Almost made that mistake. So thanks for being here. I would appreciate if you fill in the survey. Always nice to get some feedback. I heard you can win a prize. And thanks again. Enjoy the rest of Cisco Live. Nice to see you all here.